Imagine having a kind of X-ray vision, not for bones, but for the Earth itself, seeing through clouds day or night, even spotting tiny shifts in the ground.
Pretty incredible stuff.
Really is. And that's the power we're unpacking today as we take a deep dive into advanced synthetic aperture radar SAR imagery processing. Our goal, to give you a surprisingly clear handle on the cutting-edge techniques transforming how we pull value from this amazing tool. No PhD required.
Exactly. And what's really key about SAR is its use of microwave frequencies. Think of it like a different kind of light, one that punches right through things that stop normal cameras.
Like clouds.
Precisely. And it uses the sensor's own movement to create a much bigger virtual antenna. That's the synthetic aperture bit, which gives you incredibly sharp images.
Okay.
And one really insightful application, which we'll definitely touch on, is in SAR, that uses tiny differences in the radar signal's phase.
Wow, millimeter level. So we're not just getting pictures, we're getting hyper-precise measurements. But turning that raw SAR data into something useful, into intelligence, takes some serious processing power, right? Advanced algorithms.
It definitely does. That's where things get interesting and where our deep dive really kicks in. We'll explore some really innovative approaches like the range migration algorithm, RMA, that's a foundational one. We'll also look at how machine learning, specifically convolutional neural networks or CNNs, are being used to, well, basically supercharge SAR image resolution.
Sharpening the picture.
Exactly. And we'll even peek into the, frankly, mind-bending potential of quantum computing for solving some really knotty SAR problems. Think of these as sophisticated shortcuts, ways to get deeper meaning faster.
Faster insights. I like that.
We've got research papers looking at these algorithms and a PhD study that's right at the intersection of machine learning, quantum computing, and SAR.
Great. You mentioned the range migration algorithm, RMA. You said it had a surprising origin.
It really does. Its roots aren't even in radar. It actually came out of seismics engineering and geophysics, studying earthquakes, looking inside the Earth.
No way. From mapping underground structures to mapping the surface from space, that's quite a leap. So how does it handle that raw SAR data? What's it doing?
Fundamentally, RMA does a few key things. First, the sensor's moving, right? So RMA has to compensate for that motion compensation.
Okay, makes sense.
It also uses a clever mathematical technique called Stolt interpolation. Crucially, it corrects for something called wavefront curvature.
Sounds complicated.
Imagine the radar waves spreading out like ripples. RMA mathematically flattens those ripples in the data to get a sharp focus.
You mentioned it started in 2D.
That's right. Initially, it was mostly the 2D version, used for spaceborne strip map. Think of a satellite painting a long, continuous strip of the ground.
Right.
Then it got adapted for spotlight mode, where the sensor kind of stares at one specific area for longer, more detailed view.
So it's pretty versatile. What makes it such a workhorse in SAR processing then? Is it just the accuracy?
Accuracy is key, but a huge advantage is its computational efficiency.
FFTs, right? Those are super common in signal processing.
Because RMA uses 1D interpolation and FFTs, it chews through data relatively quickly, especially on parallel supercomputers. This was a big deal compared to older methods needing, well, much heavier calculations.
Faster and less resource hungry. That's vital with the mountains of data these SAR systems generate. Now, you mentioned something about a 3D version. That sounds like a whole other level.
It really was a significant step. The researchers we looked at in that 99 paper made a pioneering attempt at a 3D RMA using a 2D planar synthetic aperture, moving towards genuinely three-dimensional imaging.
What are the steps for 3D RMA?
It's a sequence. First, a 2D FFT across the spatial dimensions, then matched filtering like in 2D to sharpen things based on the transmitted pulse, then the Stolt interpolation, but adapted for 3D, and finally a 3D inverse FFT to reconstruct the actual 3D image volume.
Okay, so similar concepts, just extended mathematically.
It is a bit math-heavy. MSP is essentially a technique to approximate complex integrals. It helps find the main contributions by focusing on where the phase isn't changing rapidly. For RMA, it's useful for analyzing the algorithm, sort of understanding its behavior mathematically.
Got it. And there was also a faster variant mentioned, RMA-FAD.
Frequency domain replication and downsampling. It's basically a quick-look version for strip map data. It processes it using parameters more like spotlight mode, which drastically cuts down the data volume and processing time.
Ah, for a rapid assessment?
With RMA-FAD, you usually sacrifice a bit of image quality. You might get a slightly lower signal to background ratio. Things might look a bit noisier, and the impulse response, how sharp points look, can be a bit wider, less pinpoint.
Okay, so less pristine, but much faster. If you just need a first glance at a huge area, that could be really valuable.
In one test, standard RMA took about 3 minutes 40 seconds, used 13 megs of RAM,
Yeah.
RMA Fred, just 1 minute,
Wow.
though they did note RMA Fred had some minor inaccuracies near the sensor in that particular test.
A worthwhile trade-off in many cases, I'd imagine.
Absolutely. Research is ongoing into algorithms specifically for, say, cylindrical or spherical scanning patterns. These would complement the planar 3D RMA and open up new imaging possibilities.
RMA is this efficient, evolving foundation. Let's switch tracks now to machine learning, using CNNs for super resolution in SAR. Why do we need to boost the resolution? What's the benefit?
Super resolution, or SR, is really important in SAR for a couple of key reasons. A big one is improving co-registration accuracy.
That's lining up different images of the same place taken at different times.
Exactly, you need to overlay them perfectly, down to fractions of a pixel. If they're misaligned, you can't reliably detect subtle changes. Co-registration is vital for good in-SAR results for measuring those tiny ground movements we talked about.
Right. If the images aren't perfectly aligned, what looks like ground movement might just be image shift. Makes sense. But training these SR networks for SAR, that sounds tough. Don't you need perfect high-resolution images as ground truth to teach the network? Where do you get those for SAR?
That is the major challenge. Real, high-resolution SAR ground truth is often rare, expensive, or just plain doesn't exist for the area you're interested in. One really neat approach is called scale invariant super resolution, or SINV.
Scale invariant, how does that work? How does it get around needing that perfect HR ground truth?
SINV works on the clever idea that the way an image loses detail when you shrink it, the downsampling process is kind of predictable and doesn't fundamentally depend on the image's original scale.
Interesting.
So it learns these consistent rules of how detail is lost during downsampling, and then it essentially reverses that process.
So it learns how things get blurry, then unblurs them. What does the actual CNN structure look like?
Typically, it has a few parts. An initial layer extracts basic low-level features, and you have multiple residual blocks. These are repeating units that are really good at learning complex, reusable patterns in the data.
Ah, residual blocks. They pop up in lots of powerful networks.
There's often a periodic shuffling layer, which does the actual upscaling, putting the learned details back into a higher resolution grid in a smart way.
More sophisticated than just making pixels bigger.
It's trained using readily available low-resolution images, medium-resolution images, and sort of fake high-resolution images. These fake HR images are made by taking existing images and deliberately downsampling them using standard methods like bicubic interpolation.
Okay, so it learns from artificial examples. And did they figure out the best network design? Like how many layers, how many filters?
Yeah, they experimented quite a bit. They found performance generally improves with more layers, but it kind of plateaus around 16 residual layers.
Fishing returns.
Exactly. And bigger filter sizes, like 5 by 5 instead of 3 by 3, didn't seem to offer a significant advantage either. But increasing the number of filters in each layer did boost performance, up to about 128 filters. The sweet spot seemed to be around 16 layers, 64 filters per layer, and the standard 3 by 3 filter size.
Okay, so a reasonably deep network, but not necessarily super wide filters. Now, SAR data is complex valued, right? Real and imaginary parts. How does SINV handle that?
Good point. It processes the real and imaginary parts separately. Because they contain different aspects of the signal information, applying the SR to each part independently allows for a more accurate reconstruction compared to methods that just treat it like a standard image.
And the results, does it actually lead to better SAR images?
The research indicates strong potential, yes. SINV and similar CNN approaches seem really promising for enhancing SAR quality, especially for that critical co-registration step, which then flows through to generating better, more reliable in-SAR maps.
That's really exciting, getting more detail without needing impossible ground truth. Okay, let's push the boat out further. Quantum computing for phase unwrapping. This sounds like sci-fi territory.
So, phase unwrapping. We mentioned in-SAR uses the phase of the radar signal. The problem is the radar measures this phase like an angle, wrapped between 0 and 360 degrees.
Like the hand on a clock, you only see where it is now, not how many times it's gone around.
Exactly. But the actual information about ground height or deformation is related to the total number of rotations, the unwrapped phase. Getting that continuous phase back from the wrapped measurements is the challenge.
And why bring in quantum computers?
It can be framed as a massive optimization problem. You're trying to figure out the most likely integer number of 2 cycles to add or subtract at every single pixel to make the whole phase map smooth and consistent, especially when there's noise. For large images, the number of possible solutions explodes. Classical computers can really struggle, taking ages or getting stuck in suboptimal solutions.
Okay, a giant noisy puzzle. How does quantum computing, specifically quantum annealing, help?
Quantum annealing is a type of quantum computing tailored for optimization. It uses quantum effects, most notably quantum tunneling. Imagine trying to find the lowest point in a hilly landscape. A classical algorithm might roll into a small dip and get stuck.
Local minimum.
Right. Quantum tunneling gives the system a chance to sort of tunnel through a hill to reach a potentially deeper, better valley, the global minimum, the best solution. So it has the potential to find better answers faster for these hard optimization problems.
Tunneling through the problem space. Cool. How do you translate phase unwrapping into something a quantum annealer understands?
You reformulate it as a QUBO, quadratic unconstrained binary optimization problem.
KUBO.
It essentially maps the problem onto binary variables and defines a cost function. The quantum annealer's job is to find the configuration of those that minimizes this cost, which corresponds to the best unwrapped phase solution.
So, converting the phase puzzle into a binary optimization puzzle. And the specific hardware, like D-Wave's annealers, has its own quirks. Chimera architecture.
Yeah, D-Wave's Chimera architecture describes how the quantum bits, the qubits, are connected. And the connectivity is, well, somewhat limited. You can't always directly map every variable in your problem to a unique qubit if the problem requires connections the hardware doesn't have.
Right.
So you often need embedding strategies using multiple physical qubits linked together to act as one logical variable. This limits the size of the problem you can directly run. The paper mentioned the largest direct image patch they could handle was only about 16 by 16 pixels.
16 by 16, that's tiny compared to a typical SAR scene. How do they handle real-world sized images?
They developed a really clever workaround, superpixel decomposition. The idea is to break the big image into smaller, manageable chunks, say 16 by 16 or slightly larger.
Divide and conquer.
Unwrap each small chunk individually, potentially using the quantum annealer for those small, hard bits. Then, the clever part. Figure out how the unwrapped phases of adjacent chunks should connect. This stitching problem is also formulated as a QUBO, but at the level of the superpixels, chunks.
Ah, so using QBO twice, once for the detail within chunks, once to connect the chunks consistently. And they could even do this recursively.
Yes, for really huge images, you could apply the superpixel approach multiple times, unwrap the chunks, treat those results as bigger pixels, and then run the superpixel connection process on those. They also looked at adding a small overlap, a margin between the chunks during the initial unwrapping to help ensure consistency at the boundaries.
Makes sense. Helps smooth the joins. So did this quantum-assisted approach actually work? How did it compare to classic methods?
The results were promising. On both synthetic tests and real INSAR data, the superpixel method, especially with tuned chunk sizes and margins, performed comparably to, and sometimes better than, established classical algorithms, especially in noisy conditions. But they stressed that the current qubit limits force this decomposition. It's not yet end-to-end quantum unwrapping for large scenes.
Still, a really fascinating hybrid approach, leveraging quantum for the hard bits.
Well,
Okay, one last area. Autofocus in SAR, making sure the images are sharp. Our sources mentioned issues with the standard polar format data.
right. Autofocus tries to fix blurring caused by things like tiny deviations in the sensor's flight path or atmospheric effects. One technique is multichannel autofocus, MCA. It works on the assumption that a perfectly focused image should have some areas with very low signal return, think outside the main antenna beam.
Okay.
MCA also assumes the blurring, the defocusing is basically a one-dimensional effect.
And is that always true? The 1D blurring assumption?
That's the catch. Researchers found MCA is surprisingly sensitive if that 1D assumption is violated. And it turns out this happens even with fairly moderate data collection angles when you process the data in the standard polar format.
Huh. So the standard way of handling the data messes up the autofocus assumption even for normal operations. What's the fix?
A technique called reverse step MCA, or RMCA, it basically flips the order of some image formation steps and applies the autofocus correction in the inverse polar domain. It's a different way of representing the data where the defocusing effect acts much more like the 1D case MCA expects.
Inverse polar domain. So working in a different mathematical space before creating the final image, how does that help find those low return regions MCA needs?
It turns out that if you just take the raw polar data and do an inverse Fourier transform without first putting it onto a regular Cartesian grid, which is normally done, the resulting image in this inverse polar space naturally shows those low return areas corresponding to the antenna pattern's weaker spots.
Ah, so the structure needed for the algorithm emerges more clearly in this different domain. How do they isolate those areas then?
They use what are called attenuation windows, derived from the known antenna pattern, but viewed in this inverse polar space.
Hmm.
Applying these windows isolates the low return regions needed to constrain the RMCA algorithm.
Clever. And the payoff. Does RMCA work better than standard MCA in these cases?
Simulation showed a big improvement, yeah. RMCA significantly outperformed standard MCA, especially at wider look angles. MCA's performance dropped off quickly as the angle increased, but RMCA produced well-focused images even at 5 degrees and decent results up to 10 or 20 degrees, even with challenging phase errors.
That's a really significant difference just by changing the processing domain for the autofocus step. It sounds like picking the right constraints is key, though.
Absolutely. Finding the right number of low return constraints is important. Often you need more constraints than the number of phase errors you're trying to fix. But too many isn't always better. There are still some challenges, like handling smooth transitions in the antenna pattern, maybe needing other metrics like image sharpness to help refine it.
This has been, well, an incredibly insightful tour through some really advanced SAR techniques. We've gone from the nuts and bolts of RMA
Its efficiency and even 3D potential.
to using machine learning, SINV, to sharpen images without needing perfect
A
example.
very clever workaround.
Then into the quantum realm for phase unwrapping with superpixel.
Pushing the boundaries there.
And finally, tackling autofocus limitations like with RMCA by essentially thinking outside the standard processing box.
And what ties it all together, I think, is this drive to extract more meaningful, more accurate information from this amazing data source. These techniques are providing surprising, elegant ways to see things we couldn't easily see before.
Definitely. They're giving us shortcuts to deeper understanding, and it makes you wonder, doesn't it? As these computational methods keep getting smarter and faster, what completely new insights are just around the corner? What currently hidden patterns and remote sensing data will we unlock next, and how will that change how we see our world?
That's the exciting question. What comes next?